Righty. Hello, you 12s. Welcome to your first lesson? Lecture? Anyway, so today's a bit of a recap of what you should have learned last year. So we're looking first and foremost at measurements, units, and uncertainty specifically. Alright, so we don't have your textbook yet, so this is stuff that I covered while I was in uni. The first year in uni in physics is pretty much year 12, so this will do until you actually get your books. Alright, so first and foremost, as you know, measurement, what we use it for to measure properties of the world, we need to be able to measure fundamental properties, length, time, temperature, mass, and charge. Have a think about it. Why do we need to measure things? What's the point of measuring things? If we measure things, we can understand them, we're accurate, we can use them. I'm sure you already know, when we measure things in physics, we use the standard international units, or system international units, used by nearly every country. The exception would probably be America, because, they're still on the imperial system. So, in SI units, there are 7 base units. All other units in the SI system are derived from these 7 base units, or a combination of them, like meters per second is a unit of speed, and units have prefixes to indicate the fraction or multiple of base unit. So this here, this this table here, you should know. So quantity, what type of measurement it is, if it's length, time, mass, temperature, electric current, amount of substance or luminous intensity, what the unit is for that, so meter, second, kilogram, Kelvin, ampere, mole, or candela, and lastly what the abbreviation is. Okay, we're not so interested in this middle column here. This is more for your understanding, but we will be using the abbreviations a lot. Okay, so other systems that are commonly used, imperial system, if you're in America, so that's miles, pounds, gallons, Fahrenheit, calories, etc. The CGS, which is centimeter, gram, and second, that's basically what you were taught in middle school and early years of high school. It is best to just use one system. If you write in your prac reports or in your tests a absolute horrendous thing like $125 million Mars orbiter lost in 1992 between confusion between let's restart that. This here is an example of what can happen if you do not all use the same measuring system. They lost an orbiter because half the people working on it were American, the other half were not, and they was not a standard unit system, so the Americans were using imperial and everyone else was using metric, and the whole thing went kaput. If you want to read more on that, look it up. Alright, so fundamental unit standard. For times we have seconds. Now, how we define a second has changed over time. Previously it was 1/86,400th of a mean solar day, so your average solar day. In 1967, they changed it to, I'm not going to attempt to read that number, vibrations of a cesium-133 atom. That is the specificity of it. Okay, now the length, we use a meter or a meter ruler. In 1791, it was 1/10 millionth distance from the equator to the North Pole. In 1889, it was the distance between two lines on a planetary iridium bar in Paris. You can still go see the platinum iridium bar in Paris. It's in a museum, but as things do with time, they wear and tear, they end up shrinking a little bit, so it changed a little bit. Now it is defined as the distance light travels in a vacuum in one very big number of a second. Okay? Very precise there. Next, for weight, we use the kilogram. So, mass of a platinum iridium cylinder kept at the International Bureau of Weights and Measures near Paris. A determination of all masses can be traced back to the standard mass. Okay? Alright, so why are measurement standards important? First and foremost, uniformity of measurement across the globe. Secondly, systems that work in Australia work internationally. And good science is qualitative and reproducible. Okay? If you cannot reproduce your results in your experiments, you're not sciencing well enough. Okay? Alright, so some prefixes you need to know. These are all massive or very tiny. Okay? So your yotta, zeta, exa, peta, tetra, giga, mega, kilo, hecto, deca for your large ones, and then for your small ones, deci, milli, deci, centi, milli, micro, nano, pico, femto, atto, zepto, yocto. Okay? I'm not expecting you to remember those, but at least remember the numbers of their power to. That's all. Okay, alright. So, in physics, you'll be doing a lot of unit conversions, as I'm sure you're well aware. So, measurements of physical properties in different units have different numerical values, even if they are measured in the same thing. So, 1 meter, 100 centimeters, 39.4 inches. So we use conversion factors to switch between units. A conversion factor is a ratio expressing how many of one units are equal to that of another unit. So for example, 1 centimeter is equal to 0.01 meter, or 100 centimeters equals 1 meter. Okay, easy. That's a unit conversion. When doing calculations with many different terms, so you have like 6 or 7, important to make sure all the base units are the same. Before you do any of your calculations, make sure all of your units are the same. Okay? You want everything in meters, everything in seconds, everything in meters per second. Okay? Make sure that is all the same across the board. That is the first thing you do with any equation. Okay? Now, metric units are usually easier to convert between because they are decimalized and only vary by factors of 10, the exception being time. Time is base 60. Okay? So, I'm sure you're all aware, 1 hour is 60 minutes, 1 minute is 60 seconds. Okay, so we are going to go through an example of converting miles per hour into meters per second. Alright, so first you need the kilometer to mile conversion factor, which is, for you guys, 1.6. Okay, they're a bit more specific here, whereas 1 mile is 1.609 kilometers. If you want to remember that number, that's fine. If not, 1.6 is fine. Okay, so the conversion factor to go from kilometers to mile is 1.69 kilometers slash, so 1.69 kilometers per 1 mile is equal to 1.69 kilometers per mile. Okay, so to calculate conversion of 1 mile per hour to meters per second, if you write out the equation, this is what it looks like, right? So we have miles over hour equals miles over hour, kilometer over miles, miles over kilometers, hour over minutes, minutes over second, meters per second. That is confusing. We will go through that slowly, okay? So, when you see this massive thing, what you need to do is fill in what you know, okay? So, what we know the kilometer per hour, how many meters a kilometer is, how long we have, so how many minutes is 60 minutes, minutes is 60 seconds. Okay, so we have this and this and this and this. Put together equals that. Okay, so you're timesing the top ones all together, dividing it, timesing the bottom ones all together, then dividing it. So it's essentially 1.609 times 1,000 divided by 60 times 60, you should get that. I don't have a calculator on me, but no, wait, let me use my phone because we have technology. Okay, so 1.609 times 1,000 is, as I'm all sure you're all well aware, 1.609. That is over 60 and 60. Hang on. 60 times 60, which is 3,600. So we have that. So we divide the top by the bottom. We get the number that is also on screen there, which is 0.4469 meters per second. Okay? So, right. So finally using the conversion factor, what we have there. So we have 200 miles per hour equals 200 times the m over s equals 89.4 meters per second. Okay? Alright. There are problems like this in the questions that you'll have to do, so we can go through that step by step if need be. Alright, so dimensional analysis. We use it to keep track of the units in physical equation to help avoid errors. This technique is also known as dimensional analysis. Basically, you write out what the dimensions are and what you are using. So if the solution to an equation has a particular combination of base units, for example, meters per second for velocity, then the variables in the equation must also be arranged so that their units simplify to the same value. What does that mean? So for example, we have velocity is meters per second is equal to distance traveled, meters, over time elapsed, seconds. In other words, meters per second equals meters over seconds. If this is correct, the units would tell us that we have made a mistake. Okay, so for example, if you had written this instead, that would not be correct. Meters per second is not the same as seconds over meters. Okay, so got to make sure that you write things correctly, and that when you have the unit, if you were to write it in a formula, it would be correct. This is correct. This is not correct. Right. If you are adding and subtracting, the quantities must have the same units. For example, 5 kilometers minus 8 kilos has no physical interpretation. You literally cannot do that. Likewise, 5 kilometers minus 6 kilometers for distance is a bit for displacement. It works because displacement is a vector quantity. But for a distance, which is a scalar quantity, doesn't really work. Okay? So a lecturer writes a formula x equals vt squared, where x is a distance, v is speed, and t is time. Might they have perhaps made a mistake? Yes, they most definitely have. Okay. So if you remember the triangle that you should have learned back in year 10, distance is speed over time. This triangle here, okay? So your distance or displacement is equal to your speed or velocity times by time. So the x equals vt squared is incorrect. The t should not be squared. It should just be s equals vt. Okay? Right. So something to think about. Is a person's height different if they are lying down or standing up? How accurately can we measure a person's height? And what are the sources of measurement error? Errors are a big thing that pop up, especially when it comes to writing prac reports. So next couple slides are going to be about accuracy and precision. Okay? It is important to know the difference between the two. They are not the same thing. So accuracy is how close a measurement is to the correct value of that measurement. So how close it is, if you're looking at a target, it is how close it is to the center of the target, to the bullseye. Precision of a measurement system refers to how close the agreement is between repeated measurements. So these here are all close together, so the action has been precise. It may not be accurate because they're not at the center of the target, but they are precise because they are all near each other. So this top target here represents good mean accuracy with poor precision because these points are far away from each other. This bottom target here is good precision but poor accuracy. Good precision, close together. Poor accuracy, not near the center of the target. Okay, so some things that are sources of uncertainty. So the factors contributing to uncertainty in a measurement include limitations of the measuring device. Whenever you use a ruler or a graduated cylinder or any sort of measuring thing, there's going to be some sort of error. It's not always going to be perfect, and that's okay. We factor for that. Okay. Next is the skill of the person making a measurement. Someone who's been doing chemical experiments for 50 or 60 years is going to be much more accurate and precise with their measurements than a 10-year-old in a lab filling a beaker with water. Okay? Next, irregularities in the object being measured. If something is a weird shape or has a bump or a dip, it's going to be more difficult to measure. and any other factors that affect the outcome, which is highly dependent on the situation. If you're doing a lab and the weather's really hot, that might affect what you're doing, or it's really cold, the air pressure, lots of factors that can affect how accurate something is measured. Alright, so first and foremost, systematic errors are reproducible. Often due to the incorrectly calibrated instruments, systematic errors can be removed once the source is identified. Okay, so for example, in a machine shop, thermal expansion can affect length measurement, can be corrected for if noticed, thus it is a systematic error. Okay, so for example, an incorrectly numbered ruler, all distances greater than 2 centimeters will be measured 1 centimeter too large. Okay, so this here would actually be 2.5 centimeters, not 3.5 centimeters. I know it's not, it's an example. Okay, next, we have random uncertainty or random errors. Different every time an observation is made. You cannot reproduce a random error. Okay? That's the major defining point between the two. A systematic error can be reproduced. A random error cannot. Okay? So real world systems in particular are noisy, and this introduces random error. And noisy doesn't necessarily mean sound. It means there are other things going on that can change the outcome of a practical. So random errors can be reduced, but only by a statistical technique. Error is a misnomer here. Uncertainty is better. Uncertainty is what we use in uni. For you guys, error is correct. Alright. So, resolution uncertainty. So instruments have a finite resolution. This is another source of measurement uncertainty. For example, a ruler, the resolution is limited to the smallest division of the ruler. Usually this resolution is uncertain, taken to be plus or minus 0.5 of the size of the smallest division. For the ruler shown, plus or minus 0.05 centimeters is the absolute error or absolute uncertainty. It always has the same units/dimensions as the measurement. Okay, we don't actually have to cover this absolute and relative uncertainty because this is university stuff. It is interesting though, and I will leave this, well, I mean, I'm going to upload this PowerPoint onto DayMap for you, but you don't have to worry about calculating uncertainties. Okay, so moving on to significant figures. Do these statements make sense? Velocity is equal to the distance divided by the second. Mass equals plus. Okay, that looks like a mess. Alright, so anyway, significant figures, the digits or decimal places in a quoted measurement, or the number of digits that we know are true via accuracy/precision of the measurement. So, accuracy and precision represented by the number of significant figures and quoted uncertainty in the measurement. We're not worrying about the second one there, okay? Okay. So, significant figures, for example, 1.2345 meters, the length measurement with 5 significant figures, 532.4 meters, length measurement with 4 significant figures. But perhaps in the 1.2345 meters, we know that the last decimal place is smaller than the accuracy of the precision. Then there are only really 4 significant figures, i.e. the length is actually that instead. Okay? For year 12s, when you're writing your answers, it's usually either 2 or 3 significant figures. So there's figures after the decimal point. Yeah, the 2 or 3 after the decimal point. Okay? So uncertainty with scientific notation, for example, if 1,200 kilometers is written 1.2 times 10 to the 3 kilometers, the number of significant figures is 4. But it was written as 1.2 times 10 to the power of 3, the number of significant figures is only 2. We should still write or state the precision explicitly, since not all measurements can be made at the implied resolution. For example, with the 60 kilometers precision, 1.02 plus or minus 0.06 times 10 to the power of 3 kilometers. That's always pretty much. Alright. Approximation order of magnitude. A way of giving a number very approximately. Okay. This is what you mostly will be using. So just rounding up to the nearest power of 10. For example, the order of magnitude of 0.002 is 0.001 or 10 to the negative 3. Okay. So estimating the order of magnitude is a useful skill for sanity checks of calculations. Sanity. That doesn't make sense. Speed of a rocket is 5 times 10 to the 6. Okay, just a quick way to write things. Statistical process. So some experimental uncertainty is due to random fluctuations, sometimes environmental, sometimes due to particle nature of electrons in instruments. That's just how life is sometimes. Alright, so we can use averaging to improve our uncertainty estimates. Over a large number of repeated observations, random errors would tend to cancel each other out. That's the nature of randomness. Everything eventually becomes equal. So looking at this wonderfully messy graph, we have here this line that's straight across is the long-term average, and this blue wavy line here is the short-term average. All these bars that are here are error bars. Okay? So if you add up all the error bars, eventually you get an average that just goes flat across. Whereas these small error bars, this short-term average line here is the average of the error bars, like 1 or 2 error bars there. Okay. So if we measure a quantity x of n times, then the average of the mean value of x is given by x bar is x plus x1 plus x2 over the weight to x n divided by n. I'm sure you guys have seen this in specialist maths or maths methods. I'm not going to bore you to death with that. Okay, also we have standard deviations. Not used so much in year 11 and 12 physics, so we're going to just skip over that a bit, but you should all know how to you should know how to calculate a mean and know how to calculate a standard deviation. Once again, more math things. Okay. You should all know how to create a histogram as well. Once again, math thing. I'm sure you're going to cover that in maths. We should have already covered it already. Alright, and now we're looking at distributions. So the more students, not students, the more things you measure and get a distribution for, the more likely you're going to end up with a lovely bell curve. Okay? So, or a normal distribution Gaussian, like Gaussian look. So for a large number of measurements, the shape of the histogram approaches the normal or Gaussian distribution. The highest frequency of observations occurs at the mean. Okay? This should all be something that you have seen before. A 68.3%, approximately 2/3 with one standard deviation. So in this area here, between this line and this line here. Okay? And then with 2 standard deviations, you get 95.5%. Okay? Alright, normal distribution. As the number of samples are taken, the mean and the standard deviation head towards the popular mean and the population mean and standard deviation. Error in mean and standard deviation is calculated using this formula here. Once again, much more of a math thing. We don't really touch this in physics. Okay? Alright, so key things to remember. Be familiar with the main basic units of standard measurements. So meter, kilogram, second. Make sure you're able to convert between the units. Be able to do dimensional analysis on equations. So looking at what is needed, making sure that your formula is using the correct units so you're ending up with the right units. Understand the sources of errors, systematic versus random. Know the difference between accuracy and precision. Be able to determine the number of significant figures in a number and be able to write numbers in scientific notation. And know the difference between absolute and multiplication. The last two you don't need to worry about. This once again uni level stuff. Anyway, that's all. I hope this goes well. If you need help, let me know. Alright, bye!